Perfect. Thank you, Sebastian. And welcome, everyone. Good morning. I'm assuming everyone over there is in morning time. I'm in the evening time. So, yeah, if I say the wrong thing, I apologize. So, just a quick background about myself. My name's Tim Fawkes, obviously. I am the Chief Developer Advocate at Aerospike. I've been a developer my entire life. I think I wrote my first computer game when I was 11 and have not looked back. I've been a computer nerd the entire time. I have been an engineer for several decades. And then I joined Aerospike. I joined as our first solutions architect and basically ran the solutions architecture team and got up to a dozen people. Now I'm running developer advocacy. So talking to people about Aerospike and what it is and how it works. So I'm really technical. So if you have any technical questions or I cover something and you don't quite understand or you want to ask other questions, then please, as Sebastian says, put the questions in the chat and I'll try and get to them at the end. So one of the things as a software developer is you typically find there's a conundrum. You have three tenets. You have speed, quality, and price. And the age-old conundrum says, well, you get to pick two of them. You can't have the third, or the third one will be dictated for you. And what I'm going to try and prove in this presentation is that's not necessarily true. So what do we mean by these things? Well, Aerospike is a database, so we're going to talk in the database domain. What do we mean by speed? And speed has a couple of tenets. It has predictable latency, and I've very carefully put the word predictable in there because you can have latency, but some use cases it doesn't matter if the latency is slow. It might be 100 milliseconds is fine for my latency for a database operation. But I want to make sure that I can meet that. I want to have it predictable so there's not enough fluctuation to make sure that I don't go outside that SLA. So predictable latency is more important than low latency in some use cases. In other use cases, as we'll see, some use cases need both. It's got to be predictable, but it's also got to be blindingly fast. The other aspect of speed is throughput. It's great if I can get one transaction to go through at very predictable latency, but what if I have 1,000, 10,000, 100,000, a million, 10 million transactions? How much can I do? What does my use case require? And so that forms another tenet of speed. When we look at quality with databases, there's a whole bunch of different factors here. There's things like resiliency. What happens if a node goes down? What happens if you lose a region or a zone in a cloud environment or even a distributed data center environment? How resilient is your database? You want your application to be up all the time. And these days, everyone's application relies on data. And so if it's not a resilient database, then that becomes an issue. Consistency is an interesting one. We're all used to relational databases where they are always consistent. You've always got the latest data and it's never out of sync. But when we start looking at distributed databases like Aerospike, we start realizing that we have a cluster of nodes and those nodes hold some information. What happens if the cluster breaks, a network switch blows up and suddenly our 10-node cluster becomes 2 5-node clusters? Can we guarantee consistency? Do we have to suffer consistency in case of network failures? What features does it have? Can it do things like multi-record transactions? Can it perform encryption at rest and compression at rest? What is the quality of those features? And scalability. How high can this go? Can it store lots and lots of data or moderate amounts of data? And if it has the ability to store lots and lots of data, is there a cost to storing that data? Does it slow the application or the database down? Price is fairly obvious, but it comes down to a couple of things. One is hardware costs, and related, but not necessarily as simply as you might think, is sustainability. What is the carbon footprint of your solution? And we'll touch a bit more on this at the end of this talk. So I want to give you some examples of some customers who have deployed Aerospike and that age-old conundrum of those three tenets I just spoke about. We're going to see that they might not necessarily all apply. We want to say, we don't need a conundrum, we can have all of them. So the first customer I want to talk about is a company called Criteo based in Paris. They are an ad tech company. So effectively, they will show the ads that are seen on your browsers as you're surfing the internet, as you're doing things on your phone or your devices. you'll see ads. These are served by ad tech companies, and Criteo is a very, very large one. In their database, they have 1.2 trillion records. It's about 300 terabytes of data. Now, that data isn't just one application. That's used by 175 applications in their stack. They've got multiple different data centers, and different applications use the data in different ways. Their transaction throughput rate, remember this is the speed part we're talking about now, this is incredibly high, 350 billion transactions a day. Now, that comes down to about 10 million transactions a second, a little over, but they burst at 250 million transactions a second. Now, I almost fell off my chair when I heard this number. It's so high. What are they doing at 250 million transactions a day? That's things like, coming up to Christmas time, they're showing a lot of ads for shopping and retail. They're showing an awful lot of ads, and that's a very, very high throughput rate. That's probably the fastest we have in Aerospike, or the Aerospike customers, doing 250 million transactions a day. Now, as for the price component, when they moved to Aerospike, they had another NoSQL in there. Now, the other NoSQL wasn't fast enough, so they put a cache in front of it. It was a fairly big cache, so they had an in-memory cache and a disk-based NoSQL database. When they looked at that, they had about 3,200 nodes of combined infrastructure. Some cache, some NoSQL, but it was a big amount of infrastructure. When they moved to Aerospike, they found that Aerospike doesn't need a cache. We don't have any form of cache in front of Aerospike. Our infrastructure is so fast that we don't need it. I'm going to show you how we do that in a moment. But basically, when Aerospike went to look up at one of those records, of those 250 million transactions in a second, it did so off storage. And that read off storage was actually faster than they were getting off the in-memory cache in their previous application. They did find that the P99 writes were slightly slower than writing into the memory cache, but in their old system, they had that cache in front, so they had to make sure that they wrote into their cache, they then pushed that into their system of record, into their NoSQL, and then they had to worry about the propagation into all the other caches. So even though the P99 on Aerospike was slightly slower, the lack of the cache meant that we were much faster than the write into the other NoSQL, and they didn't have to worry about the complexities of having a cache and the propagation. So the cost of Aerospike saved them huge amounts of money. So in their case, they got the speed, the features, and that saved an awful lot of money. At scale, Aerospike tends to be this much lower cost solution because of the reasons I'll talk about later in this presentation. The next company I want to talk about is a company called PayPal. I'm pretty sure we're all familiar with this. We've all probably used PayPal. PayPal is an industry leader in fraud prevention. They have very advanced technologies. They've used neural nets for a very long time to do fraud detection. And they used to have a fairly complex system to do it. They actually had 2 Oracle RAC clusters, and sitting in front of that, they had 360 nodes of cache. Now, every time you go and do a transaction on PayPal, it runs through this fraud detection mechanism. It goes and looks up information. Because it's a neural net, it can't just go and load all the information in parallel. It's sort of a very simple decision tree, if you will. It computes the information at one node in the neural net, and then from there it goes and says, based on that result, which node do I go to next? And so it's doing these sequential reads, if you will. If they went over their SLA, and their SLA was fairly stringent, then they had to say this transaction was not fraudulent, even if they suspected it was. So it basically fell back to a very simple rules-based system. Now, this gave them a risk to the business because they could lose money when they were saying it wasn't fraudulent, but it might have been. And it gave a poor experience because no one likes having fraud on their account. And so fraudulent transactions weren't being caught if they missed their SLA. Their data scientists looked at their data and they said, we have 10 terabytes of data. If we could go to more data, we could give better fraud results. They wanted to go to about 100 terabytes. They're now at 150 terabytes. They took all that infrastructure, those 2 Oracle RAC clusters and 360 nodes of cache, and they moved it to Aerospike, and they moved it to 20 nodes of Aerospike. Now the nodes were different. They had more memory, they had more SSDs, but it was 20 nodes compared to 360 nodes of cache and 2 Oracle RAC clusters. Their data volume went from 10 terabytes to 150 terabytes, and their records went from 10 billion to 100 billion. As you can see, their throughput improved. It went from 200,000 a second to 1 million a second. Now, they were nice enough to send us some graphs. So you can see a graph on the right-hand side. This shows the speed they were running at before. Their latency previously was about 1,700 milliseconds. Sorry, 1,700 microseconds, about 1.7 milliseconds. It was pretty fast. But when they moved to Aerospike, they found that their latency dropped almost by 10 times. They're down at about 200 microseconds. Now, that's from the application going across to Aerospike, reading the information off storage, and bringing it back. And that's over 150 terabytes. It didn't matter which record they read. And if you look at the line here, so you can see that that's the Aerospike latency line. Their previous version was pretty good. It had a little bit of jitter. The latency wasn't quite constant. With Aerospike, it's almost a dead flat line. Their latency is very, very predictable. Now, what ramifications did this have on their business? Sure, they had some technological changes, but the business drivers were we were missing SLAs. Using Aerospike allowed them to meet their SLAs. So you can see, worst case before, they're getting about 98.5% of their SLA. Now they're getting 99.95 to 100% of their SLAs. They almost never miss. They could also offer a better fraud solution because they could look at more data in the same time. They could make more decisions in the same time period. Their neural nets have progressed, and they're getting a huge business benefit out of coming out of moving to Aerospike. So again, they saved money on the bottom line simply by reducing that server infrastructure, but they also improved the business processes. So they improved their top line revenue as well, simply by having the speed of a database that was really fast behind them. The last use case I want to touch on is Adobe. So we're all familiar with Adobe. Now, Adobe has a very large experience platform called the Adobe Experience Platform. This is used by about 12,000 brands around the world. They store inordinate amounts of profiles. It's not one per person. It tends to be one per device. And so they try and unify these across all the signals they get, which say, in my case, this is Tim. So they'll try and form a unified profile of what they know about Tim. In their case, they've got 31 billion of those, and they're processing trillions of requests a day. That's in the tens of millions of transactions per second. Now, they've got a very interesting architecture too. They have a central hub which contains almost all their information, but then they've got edge caches, if you will. So the unified profile or repository sits in the middle of the center, and then for speed, they go to these activation profile caches on the edge. So the personalization services are really, really fast because they're reading the data and writing the data to Aerospike at the edge. Now, Aerospike has the ability to transmit data between different clusters. So it can send the information from these edge-based clusters to these hub-based clusters. This was a new use case. We can see the sort of scale they're talking about. Trillions of requests a day or tens of millions of transactions a second, hundreds of terabytes of enterprise data. And they said it's really nice. We like the throughput, we like the latency, we like all those nice things. But what matters most to us is reliability. We don't want people to have a bad experience. We don't want things to ever fall over. We like that predictable low latency, but reliability was key. And so they really found that moving to Aerospike, they had really high reliability. Aerospike has built-in redundancy and failover. So it knows when things have failed and will just automatically compensate. That tends to be one of the huge business drivers that we get when people move from other technologies into Aerospike. All right. When I talk about Aerospike, and I've been talking about it for a very long time in my life, I tend to get two questions. And the first is, who are you? I've never heard of Aerospike. Now, you guys are on this webinar, so I'm assuming you've heard of Aerospike. My answer to that tends to be, you probably haven't heard of us, but I bet you use us on a day-to-day basis. And you can see from those three use cases that they are household names. They're products and companies that people almost certainly interact with on a daily basis. When I sprout some of these numbers, we've got customers in the multiple petabyte range, and they're doing these ridiculous amounts of numbers, like 250 million transactions a second, and their latency is incredibly like 200 microseconds. The next most common question I get is, I don't believe you. This is too good to be true. How can this happen? So I'm going to explain that. But I'm going to have to give you some technical background first to make sure everyone's on the same page. So it's going to get a bit geeky. So if you're not so technical, just fall asleep or doze off for the next couple of slides. I'll try and keep it fairly high level. When we go and store information, there's a couple of main mediums we use to store information. One is memory. And typically you put things in memory that are able to be lost. So there'll be a cache. There'll be a cache for some form of system of record, and it's a non-durable solution. The other is storage. Now, it used to be that we'd store things on rotational drives or hard drives. These days, we're all using SSDs. And almost every database says, I like SSDs, but I really want the NVMe. NVMe is a faster spec of SSD, and it's very, very common these days. All the cloud instances, for examples, have some form of NVMe attached. Now, these different storage mechanisms on the surface, they seem to have the same properties. They both store data. They can both read and write data. But there's fundamental differences which will make a difference to us later on in this presentation. So I'm going to go through some of the differences now. DRAM sits inside your computer. It sits inside the motherboard of your computer, and there's a finite number of slots that you can fill up with DRAM. Once those are filled up, you can't put any more on that motherboard. You have to go and upgrade your modules and make them bigger. Now, you can get fairly large modules these days. These days, you can get about 1 terabyte per module, but they are exorbitantly expensive. It's far more common to get, say, 124 gigabytes, 128 gigabytes or 64 gigabytes, and these fall into about $3 to $5 per gigabyte. It's also volatile. If you lose a computer, you've lost the contents of memory. It'll forget its memory very, very quickly. And it's byte addressable. I can go and look up a single byte and the memory will return me that information. Now, if I look at the SSDs, the storage on the other side, these have different characteristics. Again, they tend to sit inside the motherboard, but these sit inside what we call a PCIe slot. They tend to be white slots on your motherboard. You plug these in and you have a finite number of those. You can overcome that limitation by having what we call riser boards or multiplexing boards. The reads are much slower. So in a DRAM, it's about 50 to 150 nanoseconds or billionths of a second. A readout off an SSD is about, let's call it 100 millionths of a second or 100 microseconds. So almost 1,000 times slower. However, to compensate for that, they are persistent. So once I write information to an SSD, it stays there forever. And they're much cheaper. They're about $15 a gigabyte. I can also get fairly big drives. It's not hard to get a 30 terabyte drive. I can get one off Amazon fairly happily. And it comes in about that 15 to 20 cents a gigabyte. There's a couple of things that people tend not to know about these SSDs. One is that writes are destructive. SSDs have a shelf life because when you go and write the data, it's actually causing damage to the drive. And that's going to cause it to have a known lifetime. And when you look at the specs of an SSD, you can find out what its lifetime is likely to be based on how fast you write into that device. So they don't last forever. They're also not byte addressable. You can't go and look up a single byte. You have to do it in what they call blocks. And a block is typically 4 kilobytes. So it doesn't matter if you're reading 1 byte or 4 kilobytes, the read will take the same time because the NVMe interface forces it to read 4 kilobytes at a time. Okay, so why is that important? Well, if you go and talk to a database vendor, they will almost certainly say, we love SSDs. We run really well on SSDs. If they're not an in-memory database, they'll say we love SSDs, and particularly NVMe's, they're really fast, and we'll get a speed benefit of using an NVMe SSD compared to other drives. And they're correct. They will. The NVMe drives are typically faster than rotational drives or other sort of SSDs. But almost everyone treats an NVMe SSD as a file system, and it treats it just like a fast rotational drive. Now that's not good. There's some very, very unique characteristics of these drives. Effectively, if I'm going to write big information, let's say I've got 128 kilobytes or 128,000 pieces of information. I want to write that in one place. What I'm going to do is I'm going to say to the drive, go and write this information. And it'll go to this drive controller, which says how the drive is going to store that information, where it's going to put that information. And it will say, well, I've got multiple different dies internally on the SSD, and they can do things in parallel really, really well. So I'm going to break that up across those dies. And in my simple picture, I've got 128 kilobytes, and it's broken up across these 4 dies, each of which has, 4 channels, each of which has 8 dies in it. So I get a lot of parallelization across that, and the write occurs really quickly. Now, when I go and delete data, an SSD can't just delete a single piece of data. It has to delete what they call a block. So these blocks contain multiple records. So you can think of each one of these as a block. I can't just go and delete one, I have to go and delete all of them. So initially the drive controller will go and invalidate them and say, I've deleted this. Once I've got all of the dies in this block deleted, then I can go and reclaim the space. So if I'm going to go and delete that large data, well, I'm deleting the whole thing, and it was stored contiguously by the drive controller, so it can invalidate and go and delete the information straight away. Files tend not to act like that. Files tend to act like this picture on the right, where I get a lot of small files coming in. These go to the drive controller, and the drive controller tends to stripe them across the different channels here. So you can see that my information is small and random. When I go and delete it, I'm not deleting it out of some of those dies, but I don't have any of these that I can fully delete. So at some point, I'm going to start getting to the point where the drive controller is going to say, I don't have anywhere else to go and put this information. I can't delete any of these blocks because none of them are full, and I have to erase an entire block at a time. So what it does is it has to do what is called defragmentation. It has to merge this information together and find some information that it can delete. Now that means that it has to go and read the information, erase that block, and then go and rewrite that information elsewhere. So this causes wear and tear on the drive, because remember that writes are destructive, so the erase cycle and the write cycles are destructive on the drive. So it lowers the life cycle of your infrastructure, and it slows the drives. So any database that acts like this and treats an SSD as a faster file system is shortening the life of the drive, and it's causing a slowdown. All right, so I'm going to come back to that. So if you've paid attention, I'll come back to that, and I'll refer back to that in a moment. So I want to tell you how Aerospike works. We saw some incredible results in those use cases at the start. Petabytes, millions of transactions a second, milliseconds latencies. How do we do that? Or even microsecond latencies? Let's throw back the hood and look at how we do that. As I go through this, I'm going to sort of estimate how long things are going to take. And I've got a few assumptions. So I'm going to assume that anytime I do a network hop, that network hop round trip is going to take about 100 microseconds or 100 millionths of a second. It's pretty fast, but still, in computer terms, it takes time. Now, this assumption is not always valid. If I'm running a cluster and I've got some data in different regions, those regions are a long way apart. They might be tens, hundreds, or even thousands of kilometers apart. And therefore, the speed of light is finite, and it will add latency. So that would invalidate this assumption. I've also got things where I might be running inside the same computer, something like a Superdome Flex or some of these very large supercomputers. They have InfiniBand between them, so the networking time is much less. So I'm just using this as a ballpark figure, and it seems to be fairly accurate inside the same zone in the cloud provider and the same DC on fairly commodity hardware. The other thing that I'm going to look at is an SSD read. Anytime I read from an SSD, again, it's going to take about 100 microseconds. These, as I said before, take about somewhere between 80 to 120 microseconds. It depends on the drive and how they're doing it, and that's reading a 4K block. If something takes CPU or memory operations and only have to do it once or one set of times, then I'm going to ignore that because it's negligible compared to these other costs. If it's a small thing and I'm using a log of that, so if I've got 1 million records and I'm traversing a tree which has 1 million records in, and I'm doing it in a log structure, it's only going to do 20 memory operations. So that's almost negligible too, unless that's super large. So let me look at this. We want to look at, say, the PayPal numbers. If you remember that PayPal sent us a graph and their latency from the application to the server, look it up off storage and back, was about 200 microseconds. So let's see where they spent that budget. The first thing to know is that when Aerospike comes together, it forms a cluster. So it's got a set of nodes, and these nodes have information on. When it comes together, those nodes form a cohesive cluster, and it creates a map. And effectively what it does, it says, in this case, I've got 3 nodes in my cluster. I'm going to allocate 4,096 partitions. And I'm going to say to, when I configure Aerospike, I tell it how many copies of the data I want. And most of our use cases have 2 copies of the data. So we might have 1 master and 1 replica. And we're going to say for partition 1, the master is on A and the replica is on B. For partition 2, maybe the master is on B, replica is on C, and so on. It's a table which maps a partition ID onto a physical node. And when we write, we're always going to write to the master, and most of the time when we read, we're going to read from the master too. So if I know the partition ID, I will know which node to go to. Now this map changes over time. If I add nodes to the cluster or remove nodes from the cluster, this map can change and it will alter itself dynamically in response to adding or removing nodes from the cluster. The client also gets a copy of this cluster. When you go and connect to the cluster, your application features a rich client. And this rich client will know this partition map. We'll go and find out the cluster and say, hey, I want to know what your partition map is. Now, it's also smart. It's not just a passive library. It's going to then actively monitor the cluster so that if you start getting the addition of nodes or you lose nodes, this partition map changes. The client has to know about those changes, so it will then start picking up those changes. So even if you haven't closed your application and your cluster has added 20 nodes, your application is going to transparently go and start using those nodes because a smart client will enable it to do it. Now we want to do a single network hop from the client to the server. So we're going to incur 100 microseconds latency for that single network hop. So how do we do that? Well, it turns out it's actually pretty easy. In Aerospike, when you go and tell Aerospike you want to write a record, there's 3 key pieces of information you're going to give it. You're going to give it a namespace. Now, if you're used to relational databases, this is like a database or a table space. It's something which tells about storage and where things live. So my namespace is going to be test. Then I'm going to give it a set name, and a set is almost exactly analogous to a table in relational concepts. It's a logical grouping of records. So I'm going to go and say, I want to store this information in the test namespace in the set of customer, and my key in that set is going to be the number 1. Aerospike will take this information, the set name and the key, and it will hash them together. Now, the reason it doesn't take the namespace is that each namespace in Aerospike gets its own partition map. So it'll automatically know which one you're going to. Once we've hashed these 2 values together, we're going to get effectively random information out. We're going to get 160 bits or 20 bytes of random information. And it's random enough that we're going to call this a digest, and we can treat it as unique ID. We're going to take 12 bits of that, and that gives us a partition ID. 2 to the power of 12 is 4,096, which enables us to look up in this table computationally, without having done anything else, which node to go to. So if I have a look at the Tim record, for example, in my customer set, maybe my ID is 5, that hashes together. Maybe it gives me a number which is 2. Okay, the client has a copy of this table, goes, looks up partition 2, and says, I need to go to B, and so we'll send a network message directly to B. The client maintains connection pools to every node in the cluster. It's smart so that it knows, hey, I need to send a message to B. I don't have to go and try and reestablish a connection. It can have a minimum number of active connections, and it can grow and shrink as needed. So that's a very quick network hop, and it's very simple code to actually go and say, do that single network hop onto from the client to the node that owns that piece of data. Okay, that's well and good. Okay, so what does it do once it reaches that server? Now, I prefer our senior engineers didn't see this picture because they're going to say that is not an accurate representation of our server, and they're 100% accurate. This is a very, very simplified version of our server. And I want to give you an idea of what happens when a request comes into an Aerospike server. I'm doing a key value lookup. How do we get these latencies that are ridiculously fast? Well, for each one of those three servers I had on my previous screen, I'm going to drill into that architecture. So server A, as well as every other server, has two main components. One is an index layer, one is a storage layer. Now, Aerospike has different sort of indexes. The main one to look up a single record is a primary index. We also support things like secondary indexes and set indexes, but I won't cover them in this presentation. I want to look up my primary index. So I've got my key and I want to go and look it up by primary index. What's going to happen is we store a sprig table. So this sprig table used to be a very, very large balanced red-black binary tree. The problem was we found that it was so large that traversing that tree sometimes took too long. And so, these are customers who have very, very high density nodes. And so they're storing a lot of information. Like I had one customer who was storing 80 terabytes a node and found that they got performance issues based on this. So instead of having one gigantic tree, we broke it up into a whole set of smaller trees, and we use a hash table to find which tree to go to. This index is typically stored in memory. Now, we have different ways of storing it. We can store it on SSD, or we can store it in Intel PMEM. And this storage layer can also be in any of those mediums. It can be in memory, it can be in memory backed with disk or hard drive. It can be on SSD or in PMEM. Our most common way of accessing the data is what we call the hybrid memory architecture. And that means we're going to store the indexes in memory and the actual data on SSD. So let's assume we're talking about that. These indexes live in DRAM. That's great. Okay, so they're fast. So finding out which one of these trees to go to is fast. And these trees, because we've broken these down so each partition has its own tree, these trees tend to be very small now. So it will do some traverses of these trees to try and find the right location. When it finds it, it says, this information here is a primary index. It is 64 bytes of information. And it includes things like, how long does this record have to live? It's got a finite time to live. How many times have you changed it? And where does this record live on storage? From there, we'll go and just look up that information on SSD. You might notice I didn't say anything about a file system. Aerospike doesn't use a file system. We use these SSDs in a very low-level format. We use it in block or raw mode. So we're reading and writing directly to the SSDs. That means that we don't have any of the file system slowdowns I spoke about earlier. So this is a very, very efficient mechanism. We're traversing things in memory. They're very small trees, and we're reading off SSDs. So if I look at a read, we've got a client-server network hop. Remember, we had about 100 microseconds allocated in our budget for that. We then go and read the information of this primary index, traverse, find the tree. So in this case, it's on this tree 3. Find that information, read it off the SSD, and return it. So we've gone and spent 100 microseconds traversing that network hop from client to server, and another 100 microseconds going and reading it off the SSD. So that's about 200 microseconds. That's what we saw on the PayPal slide. So that's just returned back and works very nicely. Aerospike has a lot of things built in to try and make sure it's really fast. It's written in C, it's tuned to be memory efficient, it's optimized so that you're not getting contention and locks wherever possible. And typically we tend to find that Aerospike's bottlenecked by one of two things. It's either the storage IOPS or it's the network speed. But you might notice that I've said nothing about a cache in here. We're not reading this out of cache, we're reading this off an SSD. All right, well, what about a write? Reads are easy, okay? We're fine with that. That should be easy. What about a write? Writes are harder. Okay, I need to make sure it's consistent. So Aerospike, again, when it writes, it's going to do a single network hop from the client to the node that holds that piece of data. And then it's going to look up that information and say, I need this information stored. Is it an update to an existing record, or is it an insert into a record? And it's going to change the primary index based on that. It's going to write the record into a memory buffer. Now, these buffers aren't big. They're typically about, they're less than 8 megabytes, but it will put that information into a memory buffer. It will then go and communicate to a replica node. Remember, we want to store multiple copies of this data, and we want that data to be consistent. So we'll write to a replica node. The same thing applies on the replica node. When the replica node has the data, it will return back and say, yes, I've got it. Then we'll return back to the client. So when we say back to the client, yes, we've got it, we know that 2 machines have this data. Now, if we look at the time that's taken, again, the client serves about 100 microseconds. When we go and replicate that, it's a network hop, again, between these nodes. Remember, we're storing it in memory buffer. So the write to memory is very cheap. That network hop, again, is about 100 microseconds. We can configure Aerospike to say, how many copies of the data do you want? If we want 2 copies of the data, then great, we'll just go to one server. But if we want 3 or more copies, then these replica writes occur in parallel. So there's network message sent to both in parallel. We wait for both to respond. So again, that total time is only about 100 microseconds. All right. Now, I said that Aerospike was designed from the ground up to use SSDs. Unlike every other database, we are optimized purely for SSDs. When we do that right, this memory buffer is important. It has to be flushed to the drive, and it gets flushed to the drive either when it's full or a second has elapsed, whichever comes first. When we look at the SSD, we will break it down into chunks. Now, you tell Aerospike how big this spot buffer is. Typically, it's up to about 8 megabytes at the moment. We break the drive down into chunks of exactly that size. So every chunk in the database is, in the disk is 8 megabytes. When we go and write, we're writing the entire 8 megabytes to the drive. Now, there might be thousands of records in that 8 megabytes, but it means that we're writing those big writes to the SSD. If you remember when I spoke about the SSDs, I said that the SSDs really, really like those big writes because then they can keep them together, they can delete them and invalidate them together. And so this is really optimal for the SSDs. It creates as low write amplification on the SSD as possible. So your drives will last longer and cost you less money. They'll also be faster because SSDs will have to do less work on their defragmentation. Aerospike also uses these SSD blocks as to help with its own internal defragmentation. It gives it a very efficient defragmentation algorithm. What you'll notice also is that Aerospike does copy on write. We never update a record in place. I don't go and change a record because I might have increased its size, and that's going to cause me issues because it's in a fixed place on drive. So what we'll do is we will go and make a new copy on the write, and we'll invalidate the old copy. So over time, these use blocks become slightly emptier, and that's where the defragmentation kicks in. So there's our 200 milliseconds. We looked at both read and write. 200 microseconds for reading and writing. Now, that's not all the time. Sometimes we might have bigger records. Bigger records take more on the IOPS and they might slow down, but it's not a bad ballpark to go by. Typically, we want to look at Aerospike, and depending on the use case, we want 95 to 99% to be less than a millisecond, round trip time. So that's your throughput and your latency. But what about scaling? How do we scale this? Well, Aerospike's really designed to scale, and we don't care whether you scale vertically or you scale horizontally. In fact, what we tend to find is people start scaling horizontally, so they start with a small number of nodes. As they grow their business, they add more and more nodes. It's really quick and easy to add nodes to a cluster. But then eventually they get to a point where the cluster is big enough that management becomes an overhead. It's harder to manage 100 nodes than it is to manage 50 nodes. Obviously, things like Kubernetes operators like we have help with this, but even still, you want to make sure that your cluster doesn't grow too large. So we tend to find that people then decommission a node of their old cluster size, and they add a new one which is twice as big, particularly if you're using something like a cloud provider where it's really easy to double the node. And so they start scaling up, and they repeat that cycle over and over, scaling up and reducing the size of the cluster, and then starting to grow horizontally, and then they scale up again and again. So to support this, Aerospike has a very flexible architecture. Each node per namespace can hold up to 256 terabytes. We can make use of 4 different NICs if we need, or network interface cards, so that we can have one talking to the client, one talking between all the different nodes in the cluster, what we call the fabric, to replicate data, one to store heartbeats to know if nodes are alive or dead, and one to communicate with remote clusters for backup or offsite applications. So very efficient on scaling up and scaling out. One of the other points on scaling is we want to keep the same latency. Now, as we start adding more disks into a single node, we have more SSD space. But if you remember, I also said that Aerospike is typically constrained on SSD IOPS, the speed of the drive. Even though they're blindingly fast, that can become a limit. So what we want to do is we want to stripe the information across all the different SSDs. So if I've got 3 SSDs on 3 nodes, I've got 9 SSDs in total. Each SSD will have about the same amount of information. That means when I'm reading and writing the information, I'm doing a lot of reads and writes a second. All the nodes will have about the same load, and all the SSDs will have about the same load. So this removes any concept of hotspots. It also means that I can scale up simply by changing the SSDs inside a node. I can make them bigger, and that works really well. So I can do vertical scaling by adding CPU or memory, but most of the time your bottleneck's on the disks, so it's easy to add SSDs. And I can just take one node out of service, add an SSD to it, bring it back in service, and do that in a rolling fashion to upgrade my cluster. That's a 0 downtime. Scaling up, then that's scaling vertically. I can do the same thing scaling out by adding nodes horizontally as well. All right. So lots of good things. What's the last template I haven't covered? And that is price. We saw some examples of this. Aerospike typically reduces the amount of hardware that you need to store the same data with typically faster performance and lower cost. So if we think of the PayPal story, they increased their data by 10 times. They got almost a 10 times improvement in latency, and they reduced their hardware by a factor of 15 to do that. So let's see some of the reasons why. One of these reasons comes down to what we call replication factor. How much data do you want to store? You've got your business data. So your business might be, say, 10 terabytes of data. But if you only store one copy of it and the node that holds that one copy goes away, you've lost that data. Maybe it's blown a power supply and it's going to take a week to fix. You might only have the one copy. Sure, it might be on a persistent medium like an SSD, but it can be hard to get that data back. So typically we'll store more than one copy of data. Now, this is where common algorithms kick in. Most people who do this, and there's a lot of distributed databases who do this, use what we call quorum-based. And quorum-based is great. It sort of says, I've got 3 copies of the data. If one goes down, I still got another 2. I can guarantee consistency. Aerospike has a very unique ability where to lose one node, I only need to store 2 copies of the data. Instead of needing 3, I can only store 2. So that offers it an advantage. And in fact, as you increase the number of nodes you can lose in one hit, the advantages get bigger and bigger. So if I'm doing one, I want to be able to lose one node at a time. I'm storing 10 terabytes of business data. With Aerospike, I need 2 copies of that, so that's 20 terabytes of business data. With a quorum-based system, then I need 3 copies, that's 30 terabytes. But if I want to lose 2 nodes simultaneously, then I can, with Aerospike, I just need 3 copies of data. It's n plus 1. So I can need to store 30 terabytes. With a quorum-based system, it's 2 n plus 1s. It's actually 5 copies. So it becomes even more expensive. And you can see, as we add more copies, it becomes increasingly expensive. Now, when we're talking about a copy of the data, this could be a loss of a single node, or it could be the loss of a zone, or it could be a loss of a region, depending how you have your cluster set up. In those cases where you've got them set up for geographical failures, you'll set Aerospike up so it knows to store different copies of data in different zones or regions. Same with other databases. Now, it might sound rare to actually need 2 different outages, 2 different nodes out in different zones at the same time. So let's say I've got a 3-zone deployment, A, B, and C. I've got 3 copies of the data. Could I ever lose 2 copies of the data? It's really rare. But then you think, well, I do rolling upgrades. I want to update my software. I want to update my hardware or patch my operating system, whatever. So I'm going to take a node out of service. I'm going to do that deliberately. But then at the same time, what is the chance of me losing a node in either of those other two remaining zones? If that happens, and that's a much higher chance, then I've got an outage. I've lost 2 out of those 3 copies. Aerospike would be fine, but other databases would not be able to serve that data. So that gives us some advantages. It's 2/3 of the cost in a one node system. So a loss of one node system. So I started looking at this, and I thought it might be an interesting thought exercise to put together some actual examples of how you do this. So if we look at performance, if performance is your key driver, then you probably don't care about scalability so much. You're probably looking at Aerospike versus, say, an in-memory database. And so I put together some numbers based on instances would recommend at that low scale, so up to about, say, 20 terabytes. So Aerospike would use something disk-based, like an i4G if you're talking about Amazon. And if you're using an in-memory database, you probably want to have lots of memory, so you might use something like an R8G. I've catered for the replication factor and fragmentation of data. So Aerospike needs some room to fragment data. So does the in-memory database, but the in-memory database is typically smaller. I then looked at how many nodes we would need to do this. So for 1 terabyte of data, you can see Aerospike is dramatically smaller. As we get to bigger and bigger amounts of data, the number of nodes is ridiculously large. So Aerospike for 20 terabytes is only a handful of nodes. An in-memory database is about 300 or 320 nodes. It's really, really large. What about the fully loaded cost of that? Sure, Aerospike nodes are different. It's a different instance type. They have disks. They're probably more expensive. Well, I then went and looked at the price. Now, these prices are the on-demand pricing, not applying any discounts or anything like that. Your situation may vary. But again, you can see the cost differential, and it's actually more steep. If you look at, say, 20 terabytes, it's, I think it was about $80,000 from memory off the Aerospike one. Using it in memory at 20 terabytes with 3 copies of the data, that's 60 terabytes of DRAM without allowing for the 25% of fragmentation, you're in a lot of money. So Aerospike saves cost and it saves the nodes. Okay, that's well and good. Yeah, similar speeds, but what if we scale? What if we want something that's bigger? Okay, well, let's look at, say, Apache Cassandra. It's a very well-known, very, very scalable database. We want to do the same thought exercise. Now, in this case, the fragmentation overhead is the same. The replication factor, again, Cassandra is a quorum-based one, so it needs 3 copies. Aerospike typically needs 2 copies of the data. I went on to one of the biggest Cassandra contributors, DataStax's website, to find out what they recommended. They said an i3 8x large, this sort of use case. Now, that scales reasonably vertically, but Cassandra doesn't scale terribly well. A couple of terabytes, the sort of maximum you'll be able to store in a single node. Aerospike doesn't have that limit, so we went up to an i3 EN 12x large. This is about a 30 terabyte drives on it, so we're going to need a lot fewer nodes. And you can see that's reflected. You can almost not see the nodes of Aerospike. But these are expensive nodes. They're about $6 an hour on the on-demand price. But you can still see, even with that, Aerospike is still substantially cheaper than Cassandra. And so what you'll find is that Aerospike gets much better performance, particularly on Cassandra or something like that. It's designed for performance, and it's designed for that constant low latency we spoke about earlier. But it also typically saves a ton of money and has nice features that other database vendors are lacking, like multi-record transactions. So what about sustainability? We saw that Aerospike, compared to almost every other NoSQL database, has a much smaller number of nodes, irrespective of whether you're trying to do a small data volume and high throughput, or a large data volume and lower throughput. Aerospike simply needed fewer nodes to do the same work. It scaled vertically, and therefore its sustainability, its carbon footprint was substantially lower. Scaling vertically allows you to have a smaller footprint than scaling out, because you don't have as many power supplies, you don't have as many CPUs, things like that. Aerospike is also ridiculously efficient in terms of both CPU and its utilization of the drive, so it consumes less energy there. If you're interested in looking at the sustainability, these links show some very useful things. There's one where there's actually an IEEE paper written by a couple of Aerospike solutions architects, and it goes through real use cases and calculates the sustainability in terms of carbon footprint of different solutions. So very worthwhile reads if you're interested in sustainability. And with that, I'm going to open it up for any questions. If you're thinking of questions to ask and you want to join our community where you can talk to developers like myself and engineers, there's a QR code and that'll take you join our Discord community. It's totally free. Come and ask us any technical questions. Just hang out and say hi. So are there any questions? If you do have any, please type them in the chat. Sebastian, are there any questions at the moment?
Yeah, I think people are communicative, and I see questions come up. Yeah, there's one question about about the use cases. So it's what sort of use cases does Aerospike excel at?
Okay. If I had to characterize, Aerospike's really good at those real-time decisioning. So think about PayPal. They had an event come in, someone swiped their virtual credit card or made a payment. They needed to load a lot of data to be able to make a decision. And they were updating that information, but they're doing that sort of real-time decisioning. The same thing with Criteo. Someone comes in, there is space on their screen. It's a bid request for space on their screen, but they want to load as much information about that person as possible to make a decision within a very tight window. So these sort of things where you're doing real-time decisioning, and obviously in the realm of AI these days, there is an increasing need for feeding valid information into your AI systems to form cohesive responses. And so I see the need for these sort of real-time systems just increasing and the data volumes increasing over time.
Okay, I think that answers so far. I have another question coming in. If you want to try out Aerospike, is there an easy way to get started, Tim?
There are. That's a good question. So there's a couple of different ways of getting started. The first is we have a 100% free version. It's called the Community Edition, and it gives you the same engine that I've been talking about. Everything I spoke about today applies. It doesn't have all those enterprise-grade features. It doesn't have support. It doesn't have encryption at rest. It doesn't have encryption flight. It can't do multiple data centers and things like that. But if you just want to play with Aerospike, you've got a small use case, you want to try it out, the Community Edition is 100% free. If you have a slightly more complex use case and you want I want some enterprise features and I want to try it out, you can also get a free 60-day enterprise trial. Now, if you go onto our website and go onto the Try Now button, I think it is, it'll take you to a page with both of those. And as a pro tip, there are links on both of those which say, hey, I'd like to talk to an expert. And the expert is manned by myself and people who are on this Discord forum. So if you're like, hey, I want to try out SIA, play with it, but I'm stuck, there's a Calendly link to my calendar. Come and drop some time on my calendar. I'd love to have a chat with you.
Okay. I think this is good. Yeah, people. I will also send around Tim's email address, but you can also ask me any question. I will follow up today with an email, with all the links. Just one more question. We have time, very short. Tim, how do you prevent potential hash collision?
Great question. Okay, there's two answers to that. One is the probability. We use a hash algorithm which is designed for no hash collision. So it's called RIPE-MD 160. We didn't invent it. If you're really having trouble sleeping at night, there's lots of good papers on the internet about how it's so good to prevent hash collisions. It's so good, in fact, that we as mankind know of no two values that hash to the same value. So we treat that as unique. If you're really paranoid, and I did some maths once, and it's something like the probability of winning the lottery 7 times in a row back to back to get a hash collision, then there's a flag you can set which actually says, I want to send the key as well. And so I not only send the hash, but I send the key as well, and it will validate inside Aerospike whether that is a collision or not. And if you do find a collision, please let us know or write a white paper on it, and you'll invalidate a whole bunch of really useful research.
Okay, I see there are more questions, but we will follow up with this. Thank you very much. I think this has been very informative, tangible, technical. Just from our side, on our LinkedIn page, you can find a lot of information about our events. For example, we are at re-event. We have a lot of webinars, meetups, white papers coming out. Tim is doing a lot of stuff, blogging. So this is really informative. And just the next